Operational amplifiers can perform mathematical operation. That's why they're called operational amplifiers. So in this video, I'll show you one of these mathematical operations, specifically the summation and how to add multiple input voltages. So there's different configuration. You can do summation with different configuration. In here, I'm going to start off with the inverting configuration. Pretty much we'll be using the inverting input to do this summation, and the non-inverting input in this particular case will be connected to 0. So the configuration is pretty straightforward. As usual, you have to provide some sort of a feedback loop through a resistor from the output to the input, and the inputs in here are V1 and V2 are connected to two different resistors, and all of them are connected to Vn. So let's do the analysis in here. So I'll put my assumptions in here. My assumptions are the following: the IN is 0, and of course IP is also 0. Because the input resistance is infinity. VP happened to be in this particular case is 0 because we connected to ground. That means the Vn in here is also 0 because of the virtual short. Okay, so now what we're left with is some point in here that's 1 and that's 2. I'll write nodal equation at 1. Okay, and let's see how these nodal equations would look like. So these nodal equation, and of course you can say that this is Vn or V0. I'll just write it as Vn and then actually substitute that value with a 0. So this will be Vn minus V1 divided by R1. Pretty much this is the current going here, okay, and then I'm going to do the current going in here, and then the current going in here, and of course there's no current here. Okay, and then plus Vn minus V2 divided by R2 plus Vn minus V output divided by the RF for feedback, and that equals 0. So we substitute n with its value 0, so that gives me negative 1 divided by R1 V1, negative 1 divided by R2 V2, and that's negative 1 divided by RF V output, and that is equal to 0. And typically what we want is the output in terms of the input voltages, so I'll just move the V out to the other side, so that will leave me with V naught is equal to, I believe it will be a negative in here, and that's simply RF divided by R1 V1 plus RF divided by R2 V2. And this is actually why we call it the summing amplifier. So let me just zoom out a little bit, because what you will see is that the V naught, which is the output voltage, is simply some sort of a weighted sum of the input voltages. So it's V1 plus V2, not exactly, because it's just weighted. So it depends on RF divided by R1. So V1 got amplified by RF divided by R1, and V2 happened to be amplified by RF divided by R2. And because we're using the inverting case, this is why we have this particular negative in here. And that's an inverting configuration for a summing amplifier. All right, so this rule can be actually generalized to a bunch of voltage source voltage input or input voltages. It doesn't have to be just 2. You can actually expand this idea and tell me, well, here's the same exact configuration, but instead of just having V1 and V2, I have n of them. So then V naught is just simply a weighted sum of them. So because we're using the inverting, I'm going to put negative, and then all of them will be RF divided by R1 V1 plus, for example, RF divided by R2 V2. And then what we have is plus RF divided by R3 V3, and so forth, depending on how many voltage sources you have on the input, and that becomes RF divided by Rn divided by V, or times Vn. Okay, so let's solve a quick exercise utilizing this particular fact in here. So what you have in here, or what I'm showing you in here, is a summing amplifier that is summing V1, V2, and V3. And I haven't given you R1, R2, or R3, or RF for that matter. And what I have done is I told you, let's figure out these values of these resistors so that we can get this particular summation. So I need V1 to be multiplied by 3, V2 to be multiplied by 2, and V3 to be multiplied by 1. And well, the negative here comes from the inverting configuration of the summation. Now, of course, I have to give you some sort of a restriction so that you can actually compute these values. That's not enough. You'll be able to figure out some equations, the relationship between RF and R1, but that's not enough. So I'm showing you this. The reason for this will become much more apparent in a few minutes. All right, well, we know that the output is just simply negative RF divided by R1 V1 plus RF divided by R2 V2 plus RF divided by R3 V3. Okay, so now what are we looking for? We're looking for RF divided by R1 should be this value here, 3. and we're looking for RF divided by R2 to be 2, and then we're looking for RF divided by R3 to be 1. So all I've done is I took this, and that, and I just matched them to 3, 2, and 1. Alright, so we'll do those now, and I'll tell you, well, R1 is just simply RF divided by 3, and then you can tell me, well, R2 is just simply RF divided by 2, and then you can tell me, well, R3 is just simply RF. So I was able to write all these R1s, 2, and 3 in terms of the RF. And that's why I'm giving you this restriction in here. So any values or any relationship between them will give me this. So like if I chose RF to be 1 kilo ohm, I can figure out the R1, R2, R3 to satisfy this here equation. But what I have done is I told you, well, at a V0 negative 15, I want the IF to be 3 milliamp. So this particular restriction will tell you exactly what the value of RF is. So let's think about it a little bit in here. So what we have is I told you at negative 15, so if the voltage, and remember, like this VP here is 0, that means Vn is here is 0, so this is 0 volt in here. So when this here is negative 15 volt, I will know that the IF will be 3 milliamp. Okay, so what happens is now is I know the voltage across this resistor and the current through it, so I can pretty much figure out what that value is. So I can just say, well, RF is just simply V of F divided, or instead of VF, let me just write it specifically, it will be 0 minus V out divided by I of F. Okay, so let me just make sure they understand it. So this here is 0 and this is V out. So what I've assumed in here is this is the voltage that I'm looking for. Okay, so I said basically 0 minus V out, which will be negative 15, divided by the IF. And of course, because the current is going to the positive, so I have used positive in here. Alright, so we do that in here. Well, at negative 15 divided by 3 milliamp, and that will give me 5 kilo ohms. Okay, so that's a value of RF that will satisfy this equation. So now what we can do is we can just say this will be 5 divided by 3 kilo ohms. This will be 5 divided by 2 kilo ohms, which is 2.5 kilo ohms. And this will be just simply 5 kilo ohms. So now by putting these values to be those specific values, by putting these resistors to be these specific values, I'll be able to generate this particular sum or weighted sum. Alright, so here's how we use that now in terms of design. So what if I told you, you know what, I want to get rid of this positive in here. What do I do? Well, you might be thinking about it like, well, how can I get rid of that? Well, it's simple. We can cascade it with another inverting amplifier in this particular case, or with an inverting amplifier. So we can take originally whatever we have in here. Of course, this summation will be a weighted sum of V1 and V2 for this particular case. And the weighted sum will be RF divided by R1 for V1 and RF divided by R2 for V2. And then what we do is we put an inverting amplifier in here, and for this inverting amplifier we know that the gain for this stage, I'm going to call it G2, is just simply R divided by R. So I have put this resistor and this resistor to be the same, so the gain is 1, and because this is an inverting amplifier and its gain is 1, it will just basically flip the signs. So let me just do that for you. So you can simply tell me, well, the V, let me just call it here V first stage, for example. So the V first stage will be simply negative RF divided by R1 V1 plus RF divided by R2 V2, and that's basically the first stage. And in the first stage, that will be the input. V first stage will be the input, and the V output here, okay, will be just simply negative R divided by R, which is 1 times V first stage. Okay, so if you combine these two, you'll see that the V output is just simply RF divided by R1 V1 plus RF divided by R2 V2, and that's basically a summing amplifier without that negative part. Alright, what if I actually expanded this idea in here slightly, and instead of doing that, I did the following. Look, let's say what I've done is I've done the following here. So we're gonna assume that this is here is RA and this is here is RB. Okay, and what I will do is, in addition to these, I'll connect a couple of other sources in here, and I'll call plus minus, and that will be, for example, V3, and that will be R3. And similarly, I have this one here, and I have plus minus, and that will be V4, and that will be R4. So what will be the output V output in this particular case? Okay, so, well, we know what the first stage is. We just wrote it a few seconds ago. The V first stage is simply negative RF divided by R1 plus, well, times V1 plus RF divided by R2 times V2, okay? And this first stage now becomes, if you think about what this configuration is, this configuration is another summation amplifier. It's very similar to the first stage amplifier. It's just I'm adding V3 and V4 and VF first stage. And the V first stage amplification is just simply RA divided by RB. So let me just write this here. For the second stage, what I have as V out is just simply negative, and that will be RA divided by RB, V first stage. This is basically the first voltage. It's very, very similar to this case. Okay, and then plus RA divided by R3 V3 plus RA divided by R3 or R4 V4. All right, so now what I will do is I'll just take the V first stage and I'll substitute it by its value in here, and what you will get is the V output is just simply negative, I believe it will be positive RA divided by RB times RF divided by R1 V1, and I'll do that here, plus RA divided by R3 times RF divided by R2, and that will be V2, negative, I think that should be RA/RB. Let me just make this correction in here. It's the same as the other one here. RA divided by RB times RF divided, yes, that's correct. Negative RA divided by R3 V3, negative RA divided by R4 V4. So if you think about it, what we have done is I basically summed V1 and V2 from the first stage in the positive. So V1 and V2 got summed with these particular two gains. And then the V3 and V4 in here, I basically took the difference, and that's why basically here. So what I have done is I've summed signals with opposite signs, so not necessarily in the positive. So V1, V2 happen to be in the positive, and V3 and V4 happen to be in the negative, and I was able to do basically an operation, a mathematical operation of summing and subtracting. And there are other ways that we can actually do summations. For example, in here, I'm showing you one of the summing amplifier configuration that utilizes the non-inverting input in this particular case. And this is one of the configurations. There's more, but let's do the same type of analysis we've done before. So what we have is, we have the following. We have I of n is 0. We have I of p is 0. And now what we have is this voltage in here and this voltage in here. This we call Vn and Vp. And we just know that Vn equals Vp. And at this point, I don't know either of them. So what I have to do is I'll probably have to write some sort of equations to do the analysis. So I'll call this 1 and I'll call this 2 in here. So let's write nodal analysis at 1. Nodal analysis at 1 will tell me, well, it will be Vp minus V1 divided by R1 plus Vp minus V2 divided by R2 equals 0 because the IP is 0. Okay, so now what we're interested in is input in terms of outputs. So what I'll do is I'll basically isolate the Vp to one side and V1 and V2 to the other side. So that will give me 1 divided by R1 plus 1 divided by R2 Vp equals, I believe it will be 1 divided by R1 V1 plus 1 divided by R2 V2. All right, so we'll keep this here. That tells me that Vp is simply 1 divided by R1 V1 plus 1 divided by R2 V2 divided by 1 divided by R1 plus 1 divided by R2. And of course you can do algebra and clean it up a little bit, but let's keep it at that for now. Okay, so now what do we have? Well, we know that Vp is the same as Vn. So technically I can write a nodal equation in here, okay, and just equate them because I know I have the value of Vp. I just basically figure out what Vn is and I just equate them. Okay, so let's do that. Or actually, I don't need to write nodal equations because if you think about it, there's no current going through here. So what I have is I have this resistor and this resistor in series, and I know the voltage source across them is V0 minus 0. So I can just simply use voltage division rule to do that computation. So what I'll do in here is add 2, but this one is voltage division. Okay, so what does voltage division tell me in this particular case? Voltage division tells me that Vn is just simply V out times Rb divided by R A plus RB. Okay. So now what we have to do is we have to just take this part and this part and make them equal, and I'll figure out what V output in terms of V1 and V2. All right, so that tells me V out times RB divided by RA plus RB is just simply 1 divided by R1, 1 divided by R1 plus 1 divided by R2, V1 plus 1 divided by R2, 1 divided by R1 plus 1 divided by R2, V2. So you do a little bit of algebra, and what you will end up with is the following equation. V naught is just simply 1 divided by 1 divided by R1, R2, and that's basically 1 plus RA divided by RB, V1. Actually, we can do that here. I'll give you the final answer. You should be able to do that. V2 divided by R2. All right, so what we have in here is we have the following. The V naught is simply some sort of a amplification in here depending on RA, RB, and R1 and RA. And what we're doing is we're doing V1 is in the positive, V2 is in the positive, divided by R1 divided by R2. So depending on the values of R's and B and R1s and RA and RB and R2, I'll be able to just basically sum V1 and V2. So this particular one, because I have it utilizing the non-inverting input, I got the V out in terms of V1 and V2 in summation without having any negative. And of course, the same idea can be basically expanded to maybe more sources in here. Another, of course, each one of them will be connected to some sort of a resistor, another source, and you can expand this idea.